All right, so this class, I sent out a note last night about IPython notebooks so you can follow along. It's basically, I wanted to talk more about caches and cache behavior because it's very important for, especially multi-threading, multi-processing somewhat, single-threaded processing as well. It's super critical to understand memory behavior. There aren't caches on GPUs in general. There are things, there's local memory and things like caches. But when we get to GPU programming, the memory system becomes super critical in terms of what you need to understand the memory system to program a GPU efficiently. More almost than what it can do computationally, how you can get memory to the processor fast enough. All right, and understanding how you access memory and how caches do behave is part of that. All right. So understanding the cache, we don't get to say what's in the cache. We basically ask the memory system, which includes all the caches, for a particular memory address, and we get something back sometime later. All right? And the pattern of memory accesses determines what's in the cache. It's entirely the pattern, what is asked for when determines what will be in the cache. It's deterministic up to, timing, interrupts, and things like this. But the caches are also shared, so it's not just our behavior, it's other threads, other processes running. Sometimes that other access is actually just one of our other threads. It's very easy for these to not cooperate well. But in general, we don't get to say what appears where. We can only say, I want this piece of memory, and later on, if we ask for it again, hopefully it's still in the cache. That's basically what they're there for, is ask for something and then ask for it again, get it back faster. Or if we ask for something very close to it, get that back faster. So we can take advantage we can write code that's good in terms of cache behavior, and we can write code very easily that's very bad in cache behavior and basically makes them worse. Yep?
Is it only in Python you can't control what's in the cache, or is it all languages?
Pretty much all languages, even in C and assembly. I mean, in some architectures, you might be able to pin something to the cache. I don't think it's a general purpose thing, though. Okay. And I don't know which level you can pin it to. In general, you should just assume, even in C, the lowest level you're probably ever going to deal with, that the way you get something in cache is you ask for it. You can do things like pre-reads. Basically, you launch into the memory system a request for a piece of memory, but you don't actually wait for the value. Right? It's basically a sort of dependency-free memory read. It's like, I'm going to read this value very soon in the future. Please make sure it's there when I get to it. And then later on, if you do read that value, it's hopefully already in the L1. Right? But in general, you have limited control of what's in the cache. All right. Something to remember, and I'll ask some questions during this lecture. Hint, the answer is going to be this, lines. Binary caches are organized into lines of 64 bytes. That's all and the memory, just all the way down. The L1, the L2, the L3, it's just all lines. So when you read, and these correspond to some piece of memory. Basically, some 64 byte contiguous memory, starting at 0, 64, upwards, is read into the cache together, all the way from L3 up to L1. And so you always, no matter what, if you read 1 byte or an integer or a double, you get 64 bytes actually get loaded into the memory, or into the cache, right? And it's all the way down, and they have correspondences. They're always 64 byte aligned, these cache lines, all right? And this will affect a lot of the programming and a lot of the experiments we're going to do after this. So, cache lines experiment. Experiment 1, we're going to look at this. We'll see this behavior, timing things, where we're going to take an array, a fairly large array, and just increment every value, versus incrementing just every 8th value. Why every 8th, if they're in 64s? Right, lines. Basically, everything lines is going to be the answer. Exactly. 64. So in 64s are 8 bytes. So if we increment every 8th, we're still doing we're basically doing every 64 bytes. So we're incrementing something in every line, just like in the first one. In the first one, we're incrementing everything. The next one, we're going to increment 1 value in every line. So let me switch over to IPython. All right, so this is, if you're following along with what I posted yesterday, this is the Skip 8 notebook. So I just pick up, I'm going to create an array of 64 million ints. Is this big enough? Do I need to make it larger first? This what starting indexing? You mean the lines? Yes. So, well, they're 64 byte aligned. So if you see that phrase, particularly, like you hear about allocations being 64 byte aligned, it's basically when you allocate memory with malloc or something like that, it'll usually give you back something that starts on a cache line and extends forward. Anyway, so I'm going to create a 64 million int, so that's a 512 megabytes. And if I do something simple like this, I'm going to use B as a stand-in for A. In this case, B is not a copy of A. It's, because of Python, it's a reference, more or less. So it's shared the same memory. That's not so important here. Anyway, and then I increment everything. Right, so this B plus equals 1 is very fast. This drops down into NumPy, it drops into C code. The C code is basically add an integer to every value. And we see, I've got if you used IPython, there's this, if you haven't used it before, there's this very nice time it cell magic, which basically runs things in there and runs things in the cell and gives you a timing. So about 60 milliseconds to update all of those. If we do the same, well, we're going to do the same calculation. I should have cleared the output because all the surprises are gone. Oh, well, these ones aren't. We're going to do the same thing here. We're going to take every eighth, though. So note the notation here, B, A, :8. That's a view on A is the NumPy terminology. It's basically a reference to every eighth element of A. But it's still the same memory. It's not a compressed array. There's still space. So basically the elements of B are the elements of A every eighth, so every 64 bytes. And so we're doing 1/8 of the computational work here, right? When we go and increment this, we only increment every eighth value of A. Still takes the same amount of time. Takes even a little bit longer here, which is just noise in the system. We're doing far less computation, but in this case it's memory bound, right? Because we're not doing a very complex computation. We're just taking a value, adding one to it, putting it back. So it's memory bound, and memory bandwidth bound, not compute bound. So in this case, it takes almost exactly the same amount of time. All right, what about if we just do 1/16 of the work? Now we're not going to load every cache line. How much faster? Twice? Let's see. No, not twice. Still compute bound, or still memory bound. Part of this might be the other cache effects in there. It could be, loading, what? If I go and ask for every, I don't know why. I mean, there are a lot of things that could happen here, actually. It's not entirely clear why it's so much slower than you would think, right? Where it's doing, this is basically, so we know that this doesn't actually decrease the work. This one you would think would, but its random accesses to memory are just slow. Yep.
If things are memory bound, if you have less lookups, shouldn't it take a lot less time? Or what do you mean by memory bound?
So it takes a lot less time. If you do a bunch of random accesses in memory, right, then basically each one costs the latency of lookups, right? And latency is different than the actual memory for round trip time. If you've looked up something nearby, so that's probably what we're seeing here. These aren't random accesses, right? So if you go and ask for random array elements, widely spaced, and if you ask for twice as many, it will take about twice as much time because each one you've got this latency where it's basically the memory has to warm up the bank you're going to look at and things like this. It's complicated now. Memory is not a simple device. So it goes out there, and that's why we see different values for latency versus block reads from memory. I think that homepage or that web page from way back that had numbers every programmer should know. I think that talks about block read versus random access. If not, you can find the number somewhere. So this is probably the case that it's not random access, right? It's fairly contiguous. And so it could be that we don't have to pay the full latency cost. So that's what I'm expecting here is that it is semi-contiguous, And then we can see the same thing here, right? And we don't actually get, we get close to twice the speed once we do every other, or every fourth cache line. Then it starts to speed up. That could be a case where we're actually using less bandwidth.
Is the first command B equals A colon colon, is that slow? Is that the
That's not slow, actually. Yes, that's good, because the next cell addresses that. Right, so here I've already defined B. I didn't do this through all of them because you have to do this notation, because it's part of the time it command. If you've got the IPython notebook later, try this with this same notation, B plus equals 1 right here. It'll fail because of the way that the time it thing, it basically has to build a function around the cell code and then run it, and so it turns into a local reference problem. It's not critical, but I wanted it to be clear as possible. Anyway. Apparently it's not runnable anyway. Global name B is not defined. It's not slow. I thought this, I'm not sure what I missed there. It's actually pretty fast. Let me just talk about what it actually does. A is a pointer with some indexes, basically for the dimensions. It says I am a one-dimensional array, and this is how far my elements are spaced. And the A colon colon 32 says basically use the same pointer, take the element spacing, multiply by 32, store that. So it creates a very small record, and you can look at things like, you can check whether it's so if it were a copy, it would be slow, because I'd go and fetch, and then I'd build it, and then it would be contiguous, and then this would be, it wouldn't be a good experiment. But when you do it like that, when you take slices, it's fast. It doesn't touch any data. It doesn't matter how big A is. It's a fixed time thing, but it shares memory. So when I do this increment now, A has been modified as well. All right. I thought I'd fix this, but anyway, it's not the building of the array that's slow.
Is it possible that the cache was not just like loading in one cache line, but maybe two even in the beginning, and then like
It's possible that the NumPy code, or the C,
maybe just like your OS.
like pre-reads,
Yeah.
shouldn't. I mean, because there shouldn't be code in there that, basically the only way to do that is this, I forget the name of the assembly function. It's not generally exposed above, where you say, I'm going to read this soon. Sometimes if you've got something that the compiler can look at and say, oh, this is a loop, and you're going to be reading ahead, then the compiler can say, oh, okay, maybe I can do something with this. This is probably not the case, because the NumPy code underneath has to be fairly general, so it can deal with different offsets and strides, and it doesn't know how big the array is or how big it's going to be stepping each time, right? These are all going to be dynamic. Does that make sense? It's done in for loops, but it's done with the for loop step size, for example, is parameterized by the NumPy array, that header that I was talking about that is made. So it can't do as much optimization. If I have a for loop that says I'm going to go through this array and that my increment is 1, right? Then the compiler can be smart enough to say, oh, I'm going all the way through this array and I'm touching every element. So when I'm in this block, I'm going to pre-read that next block. That might happen. I can't, compilers can do all kinds of crazy things these days. In here, I'm pretty sure it can't. So I don't think it's pre-reading. I think it's more likely, I think it's actually, it's down into the memory system. It's some overhead. Some of it's overhead, right? Because if it's a very high overhead, you expect the times to just be the same. Some of it's overhead, some of it I think is that down at the very bottom in the memory itself, when you read something nearby, the nearby is farther than just 64 bytes, right? Here we're just talking about cache lines. Beyond that, it's a little different. The memory at the bottom is not as, the caches are fairly flat, and we'll see that in the next experiment in terms of their behavior. You work with larger and larger spacings, it stays about the same until you start hitting memory, and then you get contiguous benefits for reading contiguous data that extend over a wider distance in memory, and that falls off with distance. Whereas with caches, it tends to be, I'm good, I'm useless, right? It drops from fast for contiguous reads to not any faster for discontiguous reads. But memory falls off slower because of some of the, like banks and how the memory is organized down at the bottom. And I think that's what's going on here. It's harder to probe. Oops. Was there another question?
What is the dot 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 do in NumPy? I've never seen it.
Dot 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 says the whole array, basically. This was just an attempt to get around the global definition of B, so that I was trying to just, it's not critical, but it basically is the same as if I had done colon, comma, colon, comma, colon as many times as there were dimensions. It basically means everything.
Couldn't you just do B plus equals 1, or you're trying to make a copy? Is that what the difference?
I was not trying to make a copy. I was trying to get around, it's a Python thing that is like the one thing that really bothers me about Python is if you do B plus equals 1 in a function, it assumes that B is a local variable. It doesn't assume that it's a global variable. Right, so usually you can get around it by this. So if you want to increment a global variable, I could say global B. Maybe that's all I need to do here. Actually, let me try that real quick. I don't know what'll.
So it's the timing function. That's
Yeah, I don't know what's going on. Because I've definitely defined B, right? B's defined there. Whatever. Oh, no, I haven't defined B. Because all of these were only run in, hold on, I know what to do. Because the timing function wraps it in a lambda and then runs it, I never actually defined B. I was always timing my code and not actually doing anything with it. There we go. All right, so it's there. That shows it's not the overhead. Sorry. Now I know what's going on. I could probably take out the dot, dot, dot. Anyway, it's basically, I want the whole array. I want a slice. It's basically the everything slice. Okay? All right, any more about cache lines here? Okay. All right. And then just to remember to review, this is from last lecture and maybe the lecture before as well. You know, we have about 64 registers. They're very fast. L1 is about 32 kilobytes per core, 4 to 5 cycle delay time. L2 is about 10 cycles away, so about twice as far, about 8 times larger, and then going on. The point is, the caches are hierarchical, right? L1 is smaller than L2, and that's smaller than L3. L1 is faster than L2, and that's faster than L3. So let's increment every 8th integer in an array over and over for different array sizes. This will allow us to probe the size and the speed of the individual cache lines. Why every 8th integer? Lines. The answer to every question in this lecture is lines. All right, to do this efficiently, it's time for a little pre-intro to Python. All right, we're going to use Python later. You don't need to worry too much about it now, but if you do worry about it now, you won't have to worry about it later. But you're young, so this will not happen. Python is a language and a compiler. It's a superset of Python. So if you have Python code, you can put it into Python and it'll just work. But it does compile to C. So sometimes you can get a benefit. You get about 2 times benefit if you have Python code that you run it through the Python compiler, turns into C and runs. It uses all the same sort of things internally that Python would, but since it's now it's statically evaluating all this, it can be faster. It doesn't go through the bytecode interpreter and many things. But it's very easy to create C-level code and C-level speed code with Python syntax. So I just said, okay, let's update every 8th integer in an array. Let's just do, times equals 3. So here's how we'd write this in Python, right? We have some array with some length, and we're going to do this some number of times so that we wash out some of the noise in the system. So we set some offset. And then while our iteration count is still greater than 0, update the offset, increment the offset by 8, make sure it doesn't wrap over the end of the array, and then decrement. All right? This is the Python version. It looks very much like the previous one. In fact, all I've done is add a few keywords and some information. cpdef says this is a C function and a Python function, so C Python definition. And then all I've done is add type information and some memory layout, right? I've said, okay, these are all integers. The offset is an integer. And the array that notation basically means it's one-dimensional, it's contiguous in C order. That's all I've done. Yep.
Don't people generally use memory views today instead of?
That is the memory view syntax, actually.
Is it? Okay.
Yeah, that's the memory view. The NumPy syntax is much uglier. So this is the memory view. So it'll work on Python arrays as well, which almost no one uses because NumPy exists. But you could also do it with something like that. So was there another question about this? Yeah, that'll take NumPy. So NumPy supports the buffer interface. Anything that supports the buffer interface if you want to go into the technical details. C types for this, to make it fast. You don't put in, I don't think you can take actually any Python types. You mean like dict or something like this? I don't believe it can actually take those. I'd have to look. I've never used it for that. So you put in the C types, basically. You can also use the NumPy types if you have something like double or something like that. You can access them both through their C version or through the NumPy version. And sometimes the NumPy version is actually easier because basically because you can write it as Python code and check the NumPy types in Python code, and then put the NumPy types in the header after you've got it working, right? This is, you know, does everyone know the premature optimization is the root of all evil phrase? This is from Knuth. Always write your code in Python first. When you're going to be doing Python code, write Python code. It'll be slow. Make it work. Add some checks. Maybe write a few tests. It's good. Start putting in Python. Start optimizing. Same thing here. All right. There's one more. OK, so when I give it that red information, I say this is a C type, C type, C type. I've got, and this memory layout, all of that turns into pure C code. There are no Python checks. There's nothing slow here. In fact, if you were to take and translate this code to C and write it as while iter is greater than 0, brace, whatever, I don't want to write C, it would be that, it's that code inside. You can even go in and see the intermediate result, and it's that code. And you can prove this in the compiler by saying this. You will see this more. And here's that, it talks about the GIL, but really what that means is there's no Python code here. Everything below here has to be C with absolutely no reference to the Python runtime. So just by asserting this, if you haven't given all the types, this will fail. Something in here will be, I'm a Python type. You need to go and unbox me and figure out what my value is. But if you do that, it says, OK, nothing down here can be. And so that's a nice check. Once you think your code is pure C, you can add that and prove it to yourself. All right, so now, all right, wait, before I go on, Python questions from the pre-intro. Are you all raring to go and install this, I'm sure? You can deal with pointers. In general, you can just do this, right, where you give it an array and just use offsets. After you have it working, if you like, you know, if I wrote this in pointers, especially if you're dealing with multiple dimensional arrays, where you know you're going to be doing, you know, this y times the x, ij, and you wanted to do it in pointers instead, you can write it that way. But you don't have to. Okay. You would do it basically the same way when you're writing C code. Sometimes you would do it with just bracket notation, and eventually you'd say, you know, this would be faster if I used a pointer and a single offset. You can do that trick here. It just is more work. And at that point, it's getting pretty far away from Python code. All right. Cache size experiment 2. We're going to update all the values. Oh, I put the answer on the slide. Every 8th, actually, in multiply different sized arrays to probe cache size. And we're just going to do that over and over. We're going to zip through an array of like 1K and update every 8th value to touch every cache line, and then loop back through and do this a bunch of times, and then grow the array and see what sort of performance we get. All right, so back we go to IPython. This one, I think I have to do all this, yep. All right, so there's some extra noise in this IPython notebook to set up Python. All right, so first I get the timeit. I'm going to use timeit later. That's a very useful module to know. This is how I set up basically the magic in Python, or sorry, in IPython so that I can deal with Python inline. And then here's my Python code. I've got some extra stuff at the top. The C import numpy as NP lets me access numpy types as C types, things like that. So for example, here, where I declare the type for the array, I say np.int64t. So I can assert that it's 64 bytes, because you never know how big an integer is these days. Length long, it's basically the same code, a little bit different because I know I'm going to get a power of 2 array, so I'm using a mask instead of the mod function. Okay. But other than that, it's exactly what we just showed on the slides. All right. And the nice thing is, in IPython with this line, this Python cell magic, I can write Python code inline, and then it just goes off. And down below now, the C compiler, you know, it translated to C, and the C compiler ran and linked it in with Python and loaded it into my thing, and but it's it's C code that has been loaded into my Python. All right. This is just a helper function. Takes a size and then computes all the things and basically runs it. Let me make it more readable. It's going to run it 3 times each and then repeat that 5 times and give me the minimum. Why the minimum? Why not the mean?
Because Python interleaves garbage collection and stuff like that, and the mean may not actually be reflective of the time that
That's a very good answer. When I drop the GIL, garbage collection can't happen, at least in that thread. Garbage collection is a global process. That's a good answer. Basically avoid the overhead. And GC can be a huge overhead. It'll easily blow any timing measurement. Why the min versus the mean in particular, if we're talking about optimization? There might be noise in the system, there might be some other thread, but I really care about sort of the single thread performance here. So the fastest it can go is the fastest I could ever go on the hardware, right? It's not a noisy system in the sense that basically all my noise is upward, right? All my noise is gonna make it slower. None of my noise is gonna make it faster. That'd be awesome. I might try to figure out how to use more of that. But in this case, all the noise is upward, so I'm gonna take the minimum and try to get the lower bound. And that's really what my optimization should focus on. All right, so I'll run this. I'm gonna run this for basically 1024. I'm gonna do start with 1K, and then steps of powers of 2, so 1K, 2K, 4K. I compute the size in bytes, divide by 8 to get the actual sizes of the arrays I want to increment since they're 8 8-byte integers. Some number of iterations, and then I build the arrays, and I time this function on each of them. All right, you can watch it run. And already you can see from this some steps, right? It's hard to see in the digits. So let's plot. First, let me do this. Okay. So we basically have 3 regimes, right? Right here, right here, right here. 4 regimes maybe, and then up there. What are they? Anyone? Cache levels, and then finally the memory level. And if I put in the supposed numbers for my actual system, this is the L1 cache, ends right here. L2 cache ends here. L3 cache. Unclear why the L3 cache starts to fail a little bit early. It could be associativity, which we'll talk about next. And then the memory. And you see this ramping, right? Eventually it flattens out pretty quickly up there, the memory access. But there are the intermediate effects, which are possibly this sort of, the memory is actually more complicated even than we think. Anyway, you can run this on your own machine. It's probably going to be pretty similar, but you should see the same sort of regimes. You can look up for your particular machine what the cache sizes are. On Macs, you can run in the terminal syscontrol-A and grep for cache, I think is the thing, and it'll tell you all about your cache and memory sizes. All right, questions about this, about finding out the cache lines? Okay. What did I just do? Okay. Okay.
So just to clarify, the reason you're using Python is because it's faster than just using.
The reason we're going to use Python is it's faster, because we want to, and when we're doing multi-threading stuff, we want to be able to. That's not the main reason. It is nice. The main reason we're going to use Python is because it's the easiest way to get into true multi-threading with Python. Right? It's an accessible way. Right? I could have done this entire section in C, and we could have used OpenMP. I don't want to write C code. You don't want to write C code? Right. Python lets you write Python code, do a little bit of dirtying of your soul, and get C code performance. And simultaneously, that no GIL. So we're going to talk later about the GIL and how this sucks for multi-threading, right, in Python. And the readings on this, how the GIL and limits our ability to do true multi-threading in Python. But that with no GIL doesn't just say everything down here is fine to run outside of Python. It's, you don't need the GIL. And so if you have two threads, they can both be in there at the same time, right? And we'll do that. So when we are doing true multi-threading, and we'll have to deal with caches there more, because then you have two threads both accessing the same memory. That's how we'll get multi-threading. We'll do some heavy computation inside a block like that. We'll get multiple threads in there working at the same time, all right? And we won't have to do, with minimal soul damage, all right? If anyone here disagrees with me that Python is a great language, if you can argue that successfully with me, you'll get lots of points. All right, associativity. Sorry, this really, I don't want to get in a language war. I like Python. If you don't, that's fine. You might fail. All right, associativity. I don't want to dwell too much on this. It's something you have to know about for processors. It's important you actually understand it. We might not actually get through it because it is a little bit complicated. Often larger caches are associative. L1 almost never, L2 and L3 usually. And it's basically, on an L1 cache, any piece of memory can go to any part of the cache. And as long as you have sort of unused pieces of cache, you can put something else there. But when you then go and ask for something in the cache, you have to search the whole thing. Do I have this? Do I have this address in cache already? That's fine if your cache is small, but when it gets big, that is a huge amount of complexity and circuitry you have to implement to say, is this address anywhere, and then get that to me quickly. And so what they use is associative caches. Basically, every piece of memory can only go to a certain number of locations in the cache. On this thing, I think it's eight sets of 8 locations. So one piece of memory could be in one of only 8 locations based on its address, based on the low bits of the memory address, but not the smallest 6 bits of the memory address. Why? Oh, come on. What is the answer to why in this? Lines. 6 bits is 64 bytes. So it doesn't use those because those are always going to be the same. So which set it goes into is based on the low order bits, and it's still organized by lines. All right. What does that, that's a really short explanation of associativity. It doesn't make sense, does it? Actually, no. Let me do the next slide, and then I'll maybe draw a picture to explain better. So in this machine's L2 cache, we have it's 256K per core. So 256 kilobytes is 4,000 lines of data that we can store. And it's 8-way set associative. So basically, each piece of memory can be in one of 8 locations throughout the cache. It can be in any one of those. So there are 512 sets. They're independent, okay? And since it's ordered by the low order bits, those 512 possible locations times the 64 bytes, there's 32K between colliding lines. Let me show what I mean by colliding lines. All right, so somewhere down here we have memory. And I'll just draw it out as lines, right? So each one of these is 64 bytes. And then up here somewhere, with L3 in the middle, we have L2, okay? This one is also organized into lines. But, for example, the 0 memory element can only go into one of some number of places. So in this case, it was sets of 8. So it could be here, or here maybe, or here. But these are going to be evenly spaced. So 1, 2, 3, 4. 0, 1, 2, 3, probably here. All right. Should make it evenly spaced. 0, 1, 2, 3, and here, right? If I step forward here, in this case, on this cache, if I step forward to 512K, those are going to be the colliding line. That line will only go into these locations as well, right? This memory, if I access this memory element, it's going to at some point be loaded into L2, and because it's at that spacing, this one can only go here, or here, here. So basically, if I read this memory address, and then this memory address, and then another 512, and another 512, eventually, I'm gonna run out of places to put it, right? I only have a limited number. I don't get to fill up my entire L2 with memory from these offsets. Why? Are you asking about caches or the class? What? It was like sudden realization, oh no. It does this because, okay. Because suppose it could go anywhere, right? Which you would expect and hope for, right? Right. The problem is then when the CPU asks L2 for some address, I have to search everywhere, right, to see if it's there. On an L1, I can do that. A lot of L1s do that, where you can just say, you know, basically, search my entire cache. Do I have this memory? And it does it quickly, you know, in the 4-cycle offset or whatever. But when it gets really big, that circuitry is huge, right? It's basically launches to everything, but then, which the search is not hard, right? This is a parallel hardware problem. Like, do you have this address? Right, I could just have address numbers here. But the fan in, then, to bring it back, right? I could get an answer from any piece of my cache, and I might have to go there and search, you know, and it could be an element 1, it could be an element 500. And so that circuitry is complex and would be really expensive. And so what it does is, it says, no, you can only, if I ask for memory element 0, it can only be in a few places. And so, since it's only in one of 8 places, I only have to have circuitry that can combine 8 different possible yes/no answers. Does that explain? It's basically hardware simplification. In some caches where you want it to be really fast and not pay a lot of circuitry, you get direct mapped, which basically says can only be here. I get one choice, and if I read this value, I eject this and put this one there, right? That's going to have very bad cache behavior in a common use case, right, where I read every 512K byte. So they usually do something like 4 or 8 or 16 set associative, where I have some buffer in there where it could be in different locations. But it's entirely about speed and complexity first, because it's a complex circuit to bring that in, and speed, because if I do that, it gets slower. Does that answer? Okay. The other part of the why, your guess is as good as mine. All right.
Does a cache line have like metadata at the beginning that says what range of memory addresses?
Yeah. So the caches don't just hold the data; they also hold what address am I actually holding, and it can get worse. Like you get these TLBs, the translation look-aside buffer, and things like this. They're related to virtual memory and memory mapping and crazy stuff like that. You need a limited number of bytes, but well, you need the full 64. You need the address, which is going to be 64 bytes, but you chop off a little bit, and there might be other things that allow you to do even more, right? And if you do it with associativity, you can chop off even more bits because you know that I only have to look in certain locations. So the low bits select which cache bank. Anyway, but yes, there is metadata that says which part is there. All right. Good, we have time. All right. So we can see this behavior in this experiment. What we're going to do is we have an array. We have a large array. We're going to update the 0th byte, the nth byte, 2n, 3n going forward. And we're going to compare two things. We're going to compare, okay, what if I make n equal to 2 to the k, which we can see here is probably a poor choice because computers love 2 to the k, but caches collide at 2 to the k. And so, why 64 off the offset? Oh, very good. All right. Oops. So when we do this, there are two things to notice. Some values are going to be really bad. All right. Oops. Again, I have Python codes. Basically the same thing. It's going to do a slightly different problem. In this case, instead of my arrays are not going to be powers of 2, so in this case, I want to reset when the offset goes off the end. All right. But other than that, it's the same, basically. All right, and this time I'm also going to use, I want to be very explicit about sizes, so I'm going to use bytes. I'm going to make a big, all right. All right, and this one just runs. It runs, okay, let's do this offset a bunch of times for a 2K sized array, or sorry, a 1K, 2K, whatever, and then minus 64, and let's look at their ratio. I'm not gonna plot these. The values are all sort of easily visible. Two things to notice. One, never use power of 2, right? Using power of 2 minus 64, it's always slower, right? And sometimes it's multiple times slower, right? So a very common case, okay, you're processing data, you have a 1K sized record. 1K because programmers love 2 to the 10. You have a whole bunch of these. You have 1,000,000 of these in memory, or 1,000 of these, whatever fits. And you're gonna loop through them and say, okay, I'm gonna sum up the totals or something like that. I'm gonna do something iterative over this data. Worst possible case, right? You're gonna read the 0th byte, then you're gonna go to the 1K, and you're gonna hit your L2 cache associativity, you're gonna trash it, you're gonna go back for a piece of memory, it's not there, right? You've gone down and you've bumped it out of cache elsewhere. Trim it off. Make it 64 bytes smaller, make it 64 bytes larger. 3 times improvement, no code change, right? All you've done is padded with null bytes your structure. The other thing, some values are horrible. 64K, 8 times slower. It should actually be at 32K, but it's not clear why not. I couldn't figure that out. I did a lot of experiments. It could just be noise. Could be whatever. These values are also very noisy. The L2 is shared between the two. It's L2, it's per core, but it's shared between the two threads. Could be another thread is jumping in there just to print these values even. Anyway, some values are really, really bad, especially near the cache size, which is 32K. Between 64, 32, anywhere in there can be pretty bad. So this is all due to associativity. Well, not all, but almost all due to associativity, where you're hitting basically the same cache lines and asking them to store more data than they possibly can. All right? Is that clear, what happened here?
To 432K, why was there an improvement? Because I thought the L1 cache was not associated.
Why is there why was there improvement? Is this actually 1K? Or is it? The array is very large, sorry. The array is huge. It's the offset that I'm using.
Oh.
Sorry, yeah, I see. The array doesn't fit in L1. In fact, the array doesn't even fit in L2, right? But the offset that I'm using, I'm zipping through multiple times. It's just how far I step and which elements I read, right? Sometimes I'm reading, I'm reading, here, then 1K, then 1K, then eventually I hit this, right? And the other one is here and then slightly, smaller, and I just miss, or or eventually rotate back. But as I get larger, so if I do that, right? If I'm taking small steps, then I'm using some of the other cache line, some of the other sets, right? So I'm filling up more of my L2. But when I take bigger steps, right, I'm gonna hit here and then jump right to here, and that means that this one is gonna map somewhere in here. This one's gonna map here, here, right? If I step by, if it's 512K between collisions, if I step 256K, I'm only ever gonna use 2 of the sets. Now that actually turns into 6, it's 8-way set associative. So I actually have 16 lines that I can eventually load, but I'm loading way more than 16 overall because the array is huge. So I'll very quickly run out, okay?
Why does it use the L2 cache and not the L1 cache?
Right, so the address is, the array that I'm loading is 40 megabytes long. And I'm paging all the way to the end and loading and updating values. So eventually I'm gonna load more cache lines than I have in my L1 cache, so it must just run out. Right, as long as that array divided by the offset. Well, eventually, so the L1 is just fully associative. Anything can go anywhere, right? So, but it only has, I don't know how many cache lines in there, some number. And the array is really long. So once I have read to the end, basically I'm gonna read, if there are 100 cache lines in my L1 cache, 100 reads go into the L1, 101st ejects something. And it'll usually be least recently used, so the first one the next one's gonna eject another one, right? And so by the time I get to my array and go back to the beginning, none of these early values are in the cache anymore. They've been ejected by something. So the L1 is not doing anything for us here. It's all basically L2s. Well, probably, as we see, L3s. When it gets slow, that means I'm going farther away, right? So, you know, by 64K, I'm going to memory probably, or at least L3. I'm going to L3, because this will fit. What?
Smart enough to know which memory.
Well, what happens is the CPU says, I need this memory, and the L1 says, I've got it, or the L1 says, I don't have it. And if it doesn't have it, it doesn't actually say that, the CPU stalls. It says, I don't have this. If the L1 comes back, then it can start up again. If L2 comes back, if L1 doesn't, then L2 will come back. What really happens is L1 says, I don't have it, L2. L2 says, here, L1. L1 puts it in memory and then passes it on to the CPU. But it basically hangs until that memory can be used, right? So it's gonna go down the chain until it finds it, which may be down to memory, hands it back up the chain and stores it in the cache as it goes, finds a new place for it, and then hands it to the CPU.
At every step, it's already like loading data from memory into the three caches.
Yeah, so anytime it actually goes to memory, not always, but usually, it will say, okay, find a place for this in cache, right? And then if I read it right again, it'll go to L1. If I read it sometime later, it'll only have to go to L2. If I read it a long time later, L3, and forever, it's gonna go to memory again and rebuild that whole thing. But if I read a bunch of values like that, paging through the array, the L1 is gonna store the first value, but then when it runs out of, when it fills up, it's gonna eject something, right, when I do a new read. And eventually it just doesn't have anything that I've used recently.
How does this differ from direct cache?
Let me get back to you.
Direct map cache or direct map memory?
Direct map memory versus direct map cache, or, yeah.
Direct map memory, at least you take the modulo of the length of the cache.
Oh, so that's that's, okay, I see. That's basically the set is one, right? I talked about that. I think it's called, direct map. Yeah, I maybe even use that. Direct map, each memory location can only be in one location, right? So in that case, if I read, right, so the set associativity, if I have 8-way, basically, this location could go in one of 8. And suppose that we're reading this and this, yeah, right? It's gonna be fine, it's gonna go into L2. It can't put it here, right? Suppose this 0 location loads here. Then this one could load in one of the other locations. So if I'm reading this, then this, then this, and this, it'll just be, okay, I'm good, I'm good. In a direct map cache, this and this both have to map here. So if I alternate reading these, right? The first one goes in, then I read this, and this gets ejected. Right now this one is here, and when I go back to read this, I have to go to L3. Right, so the set associativity allows you some buffering, basically, for if you do happen to be reading at steps that are basically the size of your cache away, you won't have to go to L3 each time, right? It's basically just a little bit of noise. And I mean, in the perfect world, I'd be able to use fully associative, right? Where it doesn't matter what, or it doesn't matter what I'm reading, as long as I have cache space to put it in that isn't being used, I get all the benefits. But as I said, that's very complex circuitry-wise. Okay. I encourage you to download these, get Python running. You can generally just pip install Python or install it through whatever Python package manager you use, and then it should work in IPython. And then you can see, try it on we all have Macs, so we're all getting exactly the same numbers. But depending on, which one you have, you might have a bit stronger processor or something, or different cache sizes. And you can look that up, just compare to what you see here, make sure it compares correctly. All right. This is, as I said, this is somewhat critical to understand for multi-threading. The memory hierarchy is very critical for GPU computation. And so later on, luckily it's also simpler. But later on, we're gonna have to understand this and how memory behaves even more. All right, it's also simpler. It is simpler on GPUs though. So upcoming, the Gil reading discussion Monday. Python multiprocessing, I'll probably actually start Friday. But the multiprocessing should probably come before the GIL. Stay after, find me out here or in here for AWS setup if you're still having trouble with that. All right, cool, thank you.